Recognize this? Well, you should. This is one of those holograms I was desperately trying to impress you with in the last TV program. But although I showed you several ways of playing around with different holograms in that program, there's one thing I didn't show you, and that's what I want to demonstrate now. You can see that I've got the object still in position behind the hologram plate. There is light falling on the object. It's striking this mirror and being reflected down to illuminate the object. So we can see the object in the laser light. In addition to that, I've got reference beam light coming up and illuminating the hologram plate. But now, because the hologram's actually made, it's not referencing the hologram, it's actually playing it back. So when you look through the hologram, what you see is not one optical field, but two. They're superimposed. There's the optical field coming from the hologram itself and the optical field coming from the object. Now, because we've aligned the hologram plate in such a way that these two fields are exactly superimposed, then we only see one object. We don't see two objects. But concentrate now on that block in the middle. I'm putting my hand in, and I'm going to press on this block now. And as I press, fringes appear across the block. As I release the pressure, the fringes disappear again. Press again, and there are fringes. Release, they disappear. Now, the reason why we are seeing fringes is because I am deforming the object field relative to the hologram field. And when the object field is exactly 1/2 wavelength out of step with the hologram field, then we have a region of darkness because we have destructive interference. If we go further and get a whole wavelength out of step, then we get back to constructive interference. We get a bright region. So simply by counting across these fringes, we could tell by how many wavelengths I have deformed the object. Well, this is a pretty powerful technique for measuring that deformation. This technique forms the basis of holographic interferometry. In fact, the way I've been doing it here is known as live interferometry because I was seeing the fringes appear and disappear as I pressed on the block. That's a bit inconvenient. Normally, you'd want to know what the deformation was with a certain stress on the object. Now, what we could do is we could take one hologram of the object before it's stressed, and then without developing the plate, take a second shot of the hologram after it's been stressed, a sort of before and after situation. What will then happen is the fringes will be frozen into the hologram plate. Well, that's all very well when I have control over this deformation, but what happens when I have no control over it? For instance, suppose the object's vibrating continuously. How can I cope with that situation?
Well, that's the question we're going to try to answer in the rest of this program. We'll show you a number of different techniques of holographic interferometry. And between them, they're capable of looking at a wide range of vibrating objects. Now, it's commonly stressed when talking about holography that we have to eliminate vibrations to get a good hologram. So if we are actually interested in studying the vibrations themselves, we've got to somehow freeze the motion of the objects. Well, while Keith was at Loughborough, he went down the corridor to the Department of Mechanical Engineering. There they have a group of people who are concerned with problems of vibration.
Suppose this is my vibrating object. When I play that note, then the sound box of the viola vibrates. Now, can I pick up those vibrations? Can I pick up the movement in some way with a holographic system? Well, that's what we've got laid out here. The general optics is on the table. I'm going to come back to that in a few minutes. But the thing which really differentiates this system from the ones you've seen so far is the laser, which is here. The laser is a ruby laser, and what's more, it's a pulsed ruby laser. It's even more complicated than that. It actually has two pulsars in the one shot, not one. Now, each of those pulsars is about 30 nanoseconds wide, and we can separate them by somewhere between, say, 200, 300 microseconds. It's an adjustment we can make. The guts of the laser is down at the far end. Buried inside this black box is a ruby rod and a couple of xenon flash lamps. That's what all these warnings about 2,500 volts are on the side of the box. We put 2,500 volts into the flash lamp to create a bright flash of light, which generates the population inversion inside the laser. The light comes out at the end of the black box and travels down the line, and the first thing it meets is this complicated system of prisms. Now, that's designed to tap off a little bit of the light up through this complicated system of mirrors, and we're going to use that bit of the light as our reference beam. But let's follow the other beam down first. That carries straight on down and meets a couple more black boxes. Inside both these boxes is yet another ruby rod, one in each, and yet more xenon flash lamps. They're going to be fired at the same time as the basic laser part itself, and because you've got population inversion conditions in those black boxes, you'll get further amplification of the beam. Now, that beam comes out of the end of the laser here into the prism system and is deflected through a right angle, through some lenses, to this mirror. From this mirror, the light diverges away to illuminate the object down there, which is going to be me. Now, let's follow the reference in. The reference is coming down this path and meets this prism here and is deflected over there to those couple of mirrors over there. From those couple of mirrors, the path is down here to this lens, and from this lens onto this mirror, diverging over to the hologram plate here. The plane of the hologram is here. Now, at the moment, that's covered up so that we don't expose the plate to all the room lights, but when we darken the room, so take the hologram, I've got to take that cover off. Now, I'm going to position myself here in the path of the illuminating beam, and I'm going to pick up my viola. Before I do that, I'm a bit of a coward. I'm going to protect my eyes with some eye goggles, and I'm going to shut my eyes as well at the critical time. I'm sure it won't do any harm, but I'm not taking any risks. Now, if I pick up my viola, so I'm all ready, what I'm going to do is I'm going to play a note on the viola, and as soon as the note's played, we're going to give it about 3 seconds and then fire the laser. So if we could take down the lights and turn on the laser power. That's the hologram cover off, and now I'm going to start playing the note. Wait for the flash after about 3 seconds.
Well, you can certainly see a lot more information in this reconstructed hologram than you did during that brief double flash of laser light. During that brief instant between the flashes, Keith moved slightly, and we recorded 2 images of him. The dark interference fringes you see here are contours of equal motion. Now, on his shoulder and face, these fringes are rather irregular, showing some sort of irregular motion. But look at the fringes on the face of the viola. There, they're beautifully symmetric, indicating that the face is vibrating in a nice symmetrical fashion, as one would expect from a good musical instrument. Well, the Department of Mechanical Engineering doesn't generally waste its time taking holograms of musicians. This is far more typical of what they're interested in. The manufacturer of this engine sent it to Loughborough because he was interested in knowing what its vibration properties were while it was running. At Loughborough, they took a double-pulsed hologram, and this is the result. The fringes are, of course, contours of equal motion, and the way that they wiggle around across the engine is indicative of the strain set up during the running of the engine. Well, the double pulse system uses a rather complicated and expensive laser. That's not a disadvantage if we're looking at complicated objects, and the manufacturer has provided a contract which covers the costs. But to use this system for a simple, small object is rather like using a sledgehammer to crack a nut. It does the job, but it's a bit too sophisticated for the purpose. Suppose we want to look at a simple object. In that case, we'd rather prefer a simple laser system, and that's what Keith has over here to look at a loudspeaker.
Well, it doesn't look too much like a loudspeaker from the front, but that's simply because we've sprayed silver paint all around the black cone just to make it show up in the laser light. And the laser we're using is a helium neon laser, very similar to the one in your home kit, just a bit more powerful, but essentially the same. In addition to that, we've got the optical layout here. Let me put the loudspeaker down and show it to you. You'll notice we're using concrete slabs and plasticine blocks to support the optical components on. Now, I'm not going to go into the details of the optics. You've seen it all before. Essentially, we have to illuminate the loudspeaker cone and then let the light fall onto the hologram, which is this thing here. And at the same time, we must get some sort of reference light onto the hologram so that we do actually get a hologram. But there's a problem. How do we cope with the fact that the helium neon laser is on all the time? How do we freeze the motion of a vibrating loudspeaker? We don't have a pulses like we have with the Ruby system. But do we need to? Well, let me show you a hologram which was made with this setup. Now, there are certainly fringes there, so we're obviously getting some sort of hologram. But why? Let me show you something. A ruler, give it a twang. I think you can see that at the extremes of the motion, it's quite clear, but it tends to blur out in between. Now, that's what's happening here with this laser. As it vibrates, it's tending to blur out in between, but giving us the extremes of the motion.
Roughly speaking, these fringes are produced by the images of the speaker when it's at its extreme positions. The fringes are contours of equal vibration amplitude. I've oversimplified the situation by ignoring the intermediate positions of the speaker, though. And if we take them into account, the way the intensity depends on vibration amplitude is described by a Bessel function. And that makes the time-averaged holograms rather difficult to interpret.
Well, okay. Let's see if we can't find a more straightforward way of doing it. In fact, why not try and simulate the sort of setup I had with the pulse ruby laser? Why not try and chop this helium neon laser on and off? How much do you know about strobing techniques?
Well, let's look at this fan with conventional strobing techniques. If I switch it on, then the blades rapidly disappear into a blur, and one has no idea just what shape they are. I'll switch on my strobe system, and this produces short pulses of light at regular intervals. At the moment, the frequency of the pulses is different from the rotation period of the fan. But if I reduce the frequency, I can get to the situation where I match the two up, and now one pulse of the strobe occurs in each rotation. The fan appears stationary. What I've done is to freeze the motion.
Okay, let me do the same thing here. Only this time, I'm going to chop the laser beam with a disc with slots cut in it. As the disc rotates, it'll chop the beam on and off. Let me put it in place about here. And then you should be able, I'll get the wire out of the way. You should be able to see that as the light comes through the slot, it illuminates the loudspeaker and blocks it off. So we get click, 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 click as it rotates. Now, all I need to do is make sure that the rotation of this disc corresponds to the vibration of the loudspeaker, so that I get one flash of light on the loudspeaker cone at the same point of the cycle every time. Then I will record that particular position of the loudspeaker cone, say a forward position. But I've left something out, because to get fringes on the hologram, I must have a sort of before situation. This is the after situation. I want a before situation. I need some reference. And to do that, I simply put the blade here so that the light's coming through. A bit tricky, but now it's coming through. Vibrate the loudspeaker cone, and I get... No, sorry, I don't vibrate the loudspeaker cone. I leave the loudspeaker cone stationary, and now I get a hologram of the stationary loudspeaker cone. Then I vibrate it, start the rotating blade going, and I can make my second hologram, and I get fringes between the two. So I can turn the loudspeaker on here and set the fan going and get my hologram. Of course, the trouble with this system is that I've only picked up one particular position of the loudspeaker cone. We could really do with collecting the other positions as well.
Well, I can easily change the part of my fan cycle that I look at. All I need to do is to change the time at which the flash occurs in the cycle. Let me do that. If I change the phase of the flash with respect to the rotation, then I can in fact set the blaze to any particular position I want. I can adjust it arbitrarily.
And of course, I can do exactly the same sort of thing here. All I've got to do is adjust the timing of my rotating plate relative to my loudspeaker cone, and hence I can freeze a different particular position of the loudspeaker. But that's not really exactly what we want, because that means we've got to take a whole series of holograms. Really, what would be nice would be to get all the holograms all on one plate. Now, actually, there is a way of doing that, which has been used on developing loudspeakers. The trick is not to strobe the laser beam, we strobe the holographic plate. I put this rotating disc here, immediately in front of the plate. Now, it sounds a bit complicated, but let me go through it step by step. When the slit is right up against the edge of the holographic plate, then I'm going to record a slit hologram, which is equivalent to one particular phase position on the loudspeaker cone. But a fraction of a second later, the slit will have moved round a bit, and the loudspeaker cone will have moved forward a bit. So, adjacent to the first slit hologram, I get a second slit hologram, which is going to record a different phase position of the loudspeaker. Now, if I'm really clever, I can manage to adjust it so that one sweep across the whole loudspeaker with one slit corresponds exactly to one cycle of the loudspeaker cone. Sorry, one sweep across the hologram corresponds to one sweep of the loudspeaker cone. Now, in that way, it means that I'll record across the plate all the information corresponding to all the different phase positions of that loudspeaker cone. Now, I've actually got a hologram which has been made like that. In fact, it's not that dissimilar from the idea of the multiplex hologram that you saw in the previous TV program. You would normally view it by moving your eye round and looking at the different phase angles from different positions. But that's a bit tricky because it's really rather small. So we're going to use that other property of holograms, the property that there are always two images, a real image and a virtual image. Now, in order to get the real image, what I've got to do is put the hologram in the neat laser beam. Let me just move it out of the system. Okay. And then sample, first of all, one end of the hologram and move it across to the other end. And I see the fringes moving in and out as I sample different phase positions.
All the techniques of holographic interferometry that we've described so far have one thing in common. They use high-resolution film. Now, it would be a big step forward if we could, in fact, reduce the resolution requirement so that we could use conventional film. And if we could go still further, we might be able to use a television camera instead, and that would do away with the need for film processing, and we could perhaps do our measurements in real time. In fact, such systems are now available. They use what used to be the biggest problem of holography, namely speckle. You'll all have observed that with your home kit. And if I put an object in a laser beam and get the cameraman to stop down the aperture of the camera, then you can see that the object takes on a rather granular or speckled appearance. It's probably more apparent if I stick in a piece of white card, and the high reflectivity of this card makes it clearer. But notice one thing, the smooth card and the rough wood give a very similar size speckle. And notice another thing, if we change the focus of the camera and look at different planes, then the character of the speckle stays very much the same. Well, what is this speckle due to? Now, the surface of this card, which to the eye seems very smooth, is in fact, on the scale of wavelengths, rather rough. If I took a section through the card and magnified it many times, then we would see that there's a random array of hills and valleys, a very jagged surface. So when a plain laser beam comes in and hits this card, it's going to be reflected as a rather complex, ragged, random wavefront. Now, of course, the laser light is very coherent, so the light reflected from the valleys is going to interfere with that reflected from the peaks, and we'll get a very complex interference pattern set up. This interference pattern will, of course, propagate away from the object. And it turns out that in this interference pattern, there's a complete range of spatial frequencies. All the spatial frequencies are there with about the same intensity. It's just that they have random phases with respect to each other. Now, we only started to see this speckle pattern when we stopped down the aperture. So maybe we should try and look at an audio analogy to give us some clue as to why this effect occurs.
Yes, you didn't mishear us. We did say an audio analogy. You see, when we were thinking about this problem, it suddenly occurred to us that this random distribution in space and all the various spatial frequencies was very similar to what you would get with noise in a hi-fi amplifier. I mean, after all, with noise, in time, it's totally random, and we have lots of frequencies there. So I thought I'd set up a noise system for you so you could actually see what the waveform of noise looked like. Now, this is a noise box, generates noise for me. I'll turn it on, and on the screen, you can see the waveform, and through the loudspeaker, you can hear what that noise sounds like. Also in the box, I've got a set of filters, so I can cut out some of those now temporal frequencies. Suppose I turn the filter down a notch. Now, you can hear from the sound that we've lost some of those high frequencies, and at the same time, you can see on the screen that we have a display which is coarser than it was before. Still random, but coarse. Let me go one step further on the filters. Now we've got even less high frequencies coming through, temporal frequencies in this case, but less of them, and on the screen the thing is even coarser still. Now, perhaps this is what's happening in the lens.
Well, the aperture of the camera lens is acting as a low-pass spatial frequency filter. At the moment, we have the aperture set rather small, and that means that the transfer function of the lens is cutting off at a low frequency. We're losing the high frequency information. And that means that the size of the speckle is rather large. If you get the cameraman to open up the aperture again, then that will increase the cutoff frequency of the lens. We'll include the high frequency information, and that means we'll lose the speckle pattern from the image. Now, you might not have found that demonstration entirely convincing, but if you didn't, try it out with your home kit. Try reducing the aperture of your eye while squinting at something illuminated with laser information. Well, how do we actually apply this to interferometry? Remember that the holograms we looked at earlier used high-frequency carrier fringes on the plate, maybe 1,000 lines per millimeter. But the important information that we looked at, those interference fringes, only had a frequency of maybe a line per millimeter or something less. Now, we can use the speckle pattern as a carrier for that information. And one additional advantage is that we can adjust the size of the speckle pattern to suit the problem we're interested in. So the sort of thing we might do is to take a pair of speckle patterns and use a system for comparing them, and this will produce interference fringes. We can even do this live with a TV camera. We can use a system that works in real time using live fringes.